A very good day, ladies and gentlemen. I'm happy to be with you today on this virtual event to share some of the work we did over a period of 10 to 12 years with our partner, Hunt LNG, on the monitoring of the Peru LNG pipeline, and more specifically on the monitoring of and actually the detection of erosion, both from hydraulic and aeolian origin. And this work has led to the development of an estimation method for the depth of cover. I will start my presentation by introducing the Peru LNG pipeline, the PLNG pipeline, and we will review what type of geohazard this pipeline is exposed. The focus will be on hydraulic and aeolian erosion. So talking about erosion means that we have soil cover that's reducing on top of the pipeline, and an interesting parameter to find to characterize the estimation of depth of cover. So that's what the work that we have done here has been focusing on, and we will see how we can derive that information from the soil thermal response. We will then introduce how optical fiber sensors, and in particular distributed temperature sensors, or DTS, can be used in conjunction with the optical fiber communication cable to monitor, detect erosion, and estimate the depth of cover. And we will move to some case studies to illustrate our approach. So case studies, of course, from the Peru LNG pipeline. And that will lead us to some conclusions. So the Peru LNG pipeline is a 408-kilometer long natural gas transport system connecting to the TGP pipeline in Chiquinterca on the eastern slopes of the Andes, and reaching natural gas, an LNG plant on the coast of Peru. So it crosses the Andes and has some record-breaking altitude of 4,901 meters. So that pipeline is exposed to several types of threats, in particular in the first section, which is called the Sierra region. The pipeline is mainly exposed to landslides and also to erosion, so hydraulic erosion. The coastal section of the pipeline crosses a sand dune over 50 kilometers, roughly 50-60 kilometers, from valve station 10 to valve station 12. And that specific section is exposed to aeolian erosion and sand dune migration. So the sand dune migration is a challenge for the pipeline, because it can leave the pipeline totally exposed on some sections. So one mean to avoid, or to, let's say, detect and control the mechanism is to patrol the pipeline, and then by using some markers, vertical markers, it's possible to estimate, to quantify the depth of cover. That's great, but that's not very continuous monitoring. You need to have a visit, and usually they are organized every 6 months. So in between two visits, the pipeline can be exposed and threatened. The question is there a technique that allows the monitoring in an unattended way, and that allows the detection in real time of such phenomenon. So before giving an answer, I'd like to make some observation looking at nature. Nature is always our friend. First of all, we see that the temperature of the environment is changing periodically at two paces. It has a daily and a yearly change. So how does temperature changes vary as a function of depth? To respond to that question, to answer to that question, we will need to resolve the equation of diffusion, assuming that the temperature of the environment is periodic, as we have observed, and also considering that we have a uniform soil diffusivity coefficient over the whole pipeline, length, or over the length of the section of interest, and also as a function of that. So let's now look at the results of this of that investigation, of this resolution. If we look at the daily variation, we see that the temperature changes is still well defined, well observed, and periodic, 24 hours, up to 50 centimeters, up to 50 centimeters of depth. Below, it still varies, but the amplitude of the variation is very small. We are talking about a fraction of a degree, so it starts becoming a bit difficult maybe to measure it. But still, maybe we would be able to do so. But at least up to 50 centimeters, it's large enough. Below 50 centimeters, no changes. And if we look at 1 meter, it's absolutely flat. And 1 meter is the depth, or a common depth for a pipeline. Now, if you look at the yearly variation, we see that the change is almost inexistent or fade completely away, disappears for depth below than for depth larger than 10 meters. At the pipeline depth, we see changes, but it's the seasonal change. So we see that by using this observation, that there is a temperature change that can be observed at the pipeline depth, we can probably make an estimation of the depth of cover as soon as we have less than 50 centimeters on top of the cable. So that has some impact. We want to catch any temperature change on a daily basis or faster, and that would require to have temperature sensors buried in the ground over the whole pipeline length. And that's being able to monitor temperature in the ground along very long distances is not something uncommon. And actually, if you have an optical fiber cable laid, for instance, along your pipeline, and you have a DTS technology, distributed sensing technology, you can actually access that information. And it's kind of common to have optical fiber cable laid along pipeline because we use them for communication, and we find them laid near the pipe and probably at the same depth. So we can use this cable and connect a DTS interrogator, an instrument that reads the temperature in the optical fiber, or the temperature of the ground at the depth, at the position of the fiber. And then you can access all that information. Interestingly, the Peru LNG pipeline has a communication cable over the whole length, and they have experience with distributed sensing since 2008. So actually more than 10 years. And more specifically in the Sierra region, where they have implemented a DTS system for leak detection, erosion detection, and also a DSS, a distributed strain sensor for landslide detection. I will not detail the operation of the DTS in this presentation, as I have done it in another presentation about the TGP pipeline. But with this system, in the early time of the operation of the pipeline, I mean in 2010, we were able to catch several events. One of them was a narrow, especially narrow temperature event. So that's the negative peak in green on the left figure. And on the right figure, we have its time evolution. And we have significant drop, quick, and then a slow recovery of the temperature, reaching the ambient soil temperature. And that event was confirmed to be an erosion, not an erosion, excuse me, but an infiltration in a crack in the right of way. And that was taken seriously because it's the starting point of larger erosion of the right of way. Other type of event that was detected, as we can see here, we have a negative peak again, and if we look at its temporal evolution, we see that the negative peak is changing over time. And it has a kind of periodic behavior, and the periodic behavior is of 24 hours. So actually, we catch the daily change without time lag. We have seen with the thermal model that we could see a change in the amplitude and in the phase difference. Here we don't have a phase difference, meaning that the cable is exposed over about 5 meters. So we see that hydraulic erosion can be caught with such a technique. Now, the interesting thing is that we can also catch events that are related to aeolian erosion. And the system, more recently, in actually 2019, in August 2019, the system was implemented in the sand dune region of the pipeline. And soon after it started measuring the fiber, it sees several peaks at a location, at a specific location over a couple of kilometers. And one peak was kind of very large, or larger than 2 other events. It had a larger amplitude variation, temporal variation, and also a larger extension. So these 3 events actually are related to some erosion because they are periodic. And if we look on the graph here, we see that if we compare the temperature evolution in blue, which is the ambient temperature measured in the valve station 11, we can tell that actually we have this periodic behavior, and it's followed by a periodic behavior on the red curve with a time lag and a lower amplitude variation. So that's for event 1. We see similar behavior for event 2 and 3, but with a larger time lag and a much lower amplitude. So here, that means that we can make some observations. We can use probably the time lag information or the phase difference information to determine the depth of cover, that's for sure. We wouldn't use because it has a constant 24 hours and it has no other influence, so just the time lag. And because if we look at the amplitude variation, there may be other effects such as the intensity of the sun, or maybe other effects such as a day that is not so sunny. So the idea is just to focus on the temperature change and on the periodic variation and the induced time. So then if we report event 1 and 2 as well as the ambient temperature variation, we compare them and we plot and we fit 3 sinusoids, we see that we can estimate what is the time lag between the ambient temperature, event 1, event 2, and event 3 as well if needed. But here it's just event 1 and event 2. And interestingly, what we see is that we can, by adjusting the parameters of the fit and using the depth of the depth as one adjusting parameter, we can estimate what the time lag is. And so we find that it is for event 1 10 centimeters and event 2 20 centimeters. And the site inspection confirmed the order of magnitude. Now, a few months later, so we were in September, here we are in November, they started remedial works, so recovering and the areas of the pipeline that were almost exposed. And we see the time and the temporal evolution of the ambient temperature and of the temporal evolution of event 2. And we see that up to the 14, the temperature change is periodic on event 1. So no changes. But starting in the or after the 14, we saw that this periodic change is fading away. We have a strong attenuation of the temperature signal, as we can see here. So it means that here the remedial work has been successful because the dirt cover increased and was large enough to totally attenuate the ambient temperature changes. So these last comments lead me to the conclusions, and we have been using an unattended real-time measurement system to monitor the temperature along an optical fiber cable. That equipment allows the localization and the detection of erosion, but thanks to the post-processing, we can also estimate what is the depth of cover. And so by being able to detect in real time the erosion and estimate the depth of cover, we can improve and rationalize the maintenance activities. So we can eventually limit the time spent on the field, or focus the time spent on the field on the section of the pipeline where an issue is detected. But we also can confirm if some remedial works are done, that they have been completed successfully. And as a last application, we work with such a system. We work to the improvement of the integrity of the pipeline transportation system, but also we improve the integrity of the communication cable. So this is a bit all I wanted to say about the work we have done. I cannot end my presentation without thanking Peru LNG for the authorization on presenting the work, and also for supporting us and for supporting all the work. I cannot forget my colleagues, of course, and our colleagues for the stimulating and encouraging discussions. And also my thoughts go to ASME and Harpwell. I'm grateful for all the work they did to set up this conference, despite the current situation. And of course, I cannot forget you, the audience, for your kind attention. Thank you very much.